Okay, today we are going to see the periodic properties, that is, we are taking transition element, the properties of transition elements. Yesterday we have discussed about oxidation, and today we are going to continue standard electrode potential. So we know that if you are taking any redox reaction, okay, redox reaction means we are talking about in terms of both oxidation and reduction. So in a reaction, one substance which will be oxidized and another one which will be reduced. So redox reaction involves both oxidation and reduction. Okay. So next, if you are taking this redox reaction, the substance which is oxidized, the substance which is oxidized is acting as a reducing agent, and the similar way the substance which is reduced acting as a oxidizing agent. Generally, the oxidizing and reducing power of a metal, okay, it is usually determined by the standard electrode potential. So what is standard electrode potential? Standard electrode potential value. So far we can give it as the standard electrode potential value E naught. So what is this? That is, it is defined as a standard EMF of a cell. That is defined as a standard EMF of a cell containing molecular hydrogen in 1 atmospheric pressure and 273 Kelvin temperature. This is taken as a standard condition. Okay, the standard EMF of a cell containing molecular hydrogen in 1 atmospheric pressure and 273 Kelvin temperature, it is known as a standard electrode potential. Now, what you are going to do with the standard electrode potential? Okay, if you are taking the E naught value of, suppose, the standard electrode potential of a metal. So, if a metal, generally, if a metal has high, okay, if a metal has high value of the standard electrode potential, act as a reducing agent. High value, that high value means in terms of high value is a high value of negative of standard electrode potential act as a reducing agent. So reducing agent, if you are taking the reducing agent, it will be easily oxidized. Oxidized means it will be easily loses a electron. So standard electrode potential, and if any metal has a high negative value of standard electrode potential, it will be acting as a strong reducing agent that will be easily oxidized. Okay. Now next, the standard electrode potential value depends upon the following 3 factors. That is, the standard electrode potential value depends on, first one, enthalpy of element. Enthalpy of sublimation of element. I can give the symbol sublimation. This is a value. Okay. Enthalpy of sublimation of element. And second one, enthalpy of hydration of element. Second one, enthalpy of hydration of element. So I can give you hydration like this. Okay. And third one, it depends upon the ionization energy. Okay, those three factors only will determine the standard electrode potential. One is enthalpy of sublimation, second one is enthalpy of hydration, and third one is the ionization energy, IE. Okay, here I have given the list of 3D series element, that is standard reduction potential value of metals, that is E naught of M plus 2M value. Okay, just I have given all the values. If you are taking titanium to zinc, okay, so from this value we will get the point, that is when we move from scandium to zinc. Okay, so far we are taking the E naught value, that is titanium 1.63, 1.19 negative value. It is gradually it is going on decreasing. Okay, it is going on decreasing. When we take a manganese minus 1.18, actually minus 0.91, actually we are expecting a less negative value compared with that 91, but exception behavior we are getting minus 1.18. And slowly if you move from iron, cobalt, nickel, instead of getting negative value for copper, you are getting only a positive value plus 0.34. Again for zinc we are getting a negative value minus 0.74. So if you are taking this value, you are not expecting the regular trend, that is decreasing or increasing like that. What is the reason for that we are going to discuss. So let me take first one. When we move from titanium to zinc, we are expecting a regular decreasing in trend, but we are not following the regular trend. What is the reason for that? So if you are taking scandium, titanium, vanadium, so generally if you take the sum of ionization energy, because we are talking about the conversion of a divalent cation to metal. So we have to consider the two ionization enthalpy. One is first ionization and second ionization. So if you take the sum of ionization IE1 and IE2, including, okay, that is del sublimation value, that is enthalpy of sublimation value, we are not expecting the regular trend. It is not varying when we move from. But anyway, there is somewhat the trend is following up to some values because of the increasing in the enthalpy, that is increase in IE1 and IE2 value, generally increase in IE1 and IE2 value. This is the normal case. So next what we are going to follow is next as we move down, just we are taking manganese. So if we are taking manganese, usually we are expecting less negative value, but we are getting minus 1.18. This is the exception. So what is the reason for getting the electrode, that is standard electrode potential of Mn plus 2 and Mn value? Okay, so this exception behavior we are getting more negative value. The reason is due to off-filled electronic configuration. So where the off-filled in d orbital. Okay. Okay, so if you are taking manganese, the general order electronic configuration will be 3d5 4s2. So just we are taking 3d subshell, how many electron? There are 5 electron. In S there are 2 electron. This is in the case of metal. So if I am taking Mn plus 2, there should be removal of 2 electron. So you are going to get only 3d5. So we should take only 5 electrons in the d orbital. Okay, so due to the presence of 5 electrons or off-filled d orbital, you are going to get the standard electrode potential of a manganese to manganese ion to manganese is very high. That is, negative value is high. Okay, and next, if I am taking copper. So if I am taking a copper, the copper is getting a positive value. That is, if I am taking E0 value of Cu plus 2Cu, you are getting a positive value. So what is the reason for getting positive value means, if I am taking the sum of, that is sum of ionization, first ionization energy and second ionization energy, and usually we are adding the sublimation, enthalpy of sublimation. Okay, the sum of those value is not counterbalanced. Okay, it's not counterbalanced in, okay, comparing with counterbalanced with hydration enthalpy, with hydration enthalpy. Okay, because of getting low hydration enthalpy value. Okay, so usually we should get the sum of ionization energy and sublimation of that is enthalpy of sublimation is not counterbalanced with the low value of enthalpy of hydration. For this reason only we are getting copper 2 plus converted into copper value. We are going to get the standard electrode potential value positive. Okay, and we are discussing like this. Okay, and one more, if we are taking metal, any metal, we are getting negative value. All the metal negative value with the exception only one is copper positive. Except copper, all element in the 3D transition series shows a negative value, that is low compared with the hydrogen, because the E0 of a hydrogen, that is E0 of hydrogen is 0. Okay, so comparing with the more electronegative value, it is assumed to be 0. And from that you will get 1 point, except copper. Okay, except copper. If you are taking this except copper, other element, okay, other metal reacts with any dilute acids. Any dilute acids liberates hydrogen. Liberates hydrogen because of the hydrogen electrode potential 0 value. Okay, now I will give an example. If I am taking copper, so copper, when it is reacts with nitric acid concentrator, nitric acid, so any, just you can take dilute or a concentrated. I am taking concentrated. So copper react with nitric acid generally. So you will get copper nitrate plus nitrogen dioxide and water should be eliminated. Okay, if I am balancing this, you will get like this. Okay, from that, one point is clear. Whenever metal having a positive electrode potential reacts with the acids, okay, the liberation of hydrogen does not take place. Instead, you will get a water. Suppose if you are having zinc is having a what value? More negative value. So this zinc reacts with any dilute acid. Like for example HCl, you will get ZnCl2 zinc chloride and hydrogen gas is liberated. So from that a low, that is negative value metal will react with the dilute acid liberating a hydrogen, but the positive value copper do not liberate a hydrogen. Okay, so if you balance this ZnHCl Cl2, so 2 HCl will be possible. Okay, next we are going to see the standard electrode potential trends in that is M+2. That is standard electrode potential for the reduction of a trivalent cation to the divalent cation. Okay. So first I will list out some of the reaction, the standard electrode potential value. First we will take a reaction involving, that is standard electrode potential value. Like I will give you E0 for this reaction. Okay. So first we will consider about titanium. Okay. So titanium, to convert titanium plus 3 to titanium, okay, titanium plus 2, that involves reduction. The E0 of a particular value is 0. If you are taking 0.37, that is negative value. So for titanium, just the E0 value is minus 0.37. And if you are taking vanadium 3 plus converted into vanadium plus 2, okay, so we will get minus 0.26, that is slowly decreasing. And for chromium conversion 0.47, it is gradually increasing. And if I am taking manganese plus 3 to manganese plus 2, you will get a positive value 1.81 electron volt. Next, if I am taking iron, you will get a positive value 0.77 volt. Okay, if I am taking cobalt series conversion of cobalt plus 2, you will get a positive value 1.91. Like this E0 value is given. So based on this, if you plot the plot in the form of a graph, that is E0 value of M plus 3 to M plus 2 trends, the graphical representation, I will show you like this. If I am going with minus value 0.5, okay, so if I am taking this will be 0, you will get a positive value 0.5, 1, 1.5, 2, like this. For scandium, minus 0.37. So if I am taking for scandium, for titanium, you will get 0.37, you get this value. And for vanadium, minus 0.26 for vanadium. So if I am taking this is vanadium, like this. For chromium, minus 0.47, you will get again a drop for chromium, okay, like this. And for manganese, 1.81. So for manganese, if I am taking, this will be 1.81, like this for manganese. And for iron, there is again drop 0.77 for iron. So you will get iron 0. And for cobalt plus 1.91, so again you will get the increased value for cobalt. Okay, so if you take a graph like this, you are going to get the increase, decrease and gradual increase. This is a graphical representation of a electrode potential, standard electrode potential value versus again the transition metals in the conversion of metal cation, that is trivalent cation to the divalent cation. Okay. So here when we take titanium, vanadium and chromium. So if I am taking titanium, vanadium, chromium. So even though the trend is not in a regular way because minus 0.37 to 6 minus value, and again there will be sudden increase 0.47. So anyway, titanium, vanadium, chromium. Okay, so this is if you want to reduce chromium plus 3. Okay, if you want to reduce chromium plus 3, you have to select a metal with a high electrode potential value, high negative electrode potential value. If you want to reduce chromium, okay, chromium, reduction means if you want to reduce just we are adding a electron, it is converted into chromium plus 2. Again if you are adding a electron, again it will be converted into chromium. Okay, so generally if you want to reduce chromium 3 plus ion, more electrode potential, okay, value, metal you have to select, metal you have to select. Okay, so when we take this, okay, which metal, that is to reduce the chromium 3 plus, the metal we are choosing is zinc. The value for zinc is minus 0.74 volt, that is standard electrode potential value for zinc is minus 0.74. So more negative value of standard electrode potential metal only we can use to reduce the chromium 3 plus into chromium. So more stable configuration, the chromium more stable, and in order to reduce the chromium 3 plus we have to apply a more electronegative potential metal as a reducing agent. Okay, this is one situation. And next when we take manganese, so generally it is decreasing, but the manganese usually getting what general trend only negative, but exception we are getting plus value. What is the reason? If I am taking electrode potential of manganese, that is manganese in the form of plus 3 to plus 2 is positive. What is the reason for that? Okay, so here it is due to the electronic configuration of manganese plus 2. If I am taking manganese plus 2 configuration, you will get only 3d5. That is in d orbital we are getting only 5 electrons. So this is half-filled electronic configuration. Because of the half-filled electronic configuration, the standard electrode potential of a manganese is more positive. Okay, this is one reason. And if I am taking a iron, so iron also getting positive value but somewhat less compared with the manganese. Okay, so the electrode potential of a iron converted into iron plus 2 also positive, but low value of positive. This is due to the electronic configuration of a Fe3 plus. If I am taking Fe3 plus, usually iron is what, 3d6 4s2. So if I am taking iron plus 3 also, 3d5 configuration possible. So because of the half-filled electronic configuration, this standard electrode potential of iron is positive. And one more thing, if I am taking a cobalt, okay, again the positive value is increased. So if I am taking a cobalt value, that is the cobalt in the form of plus 3. So usually cobalt means if I am taking next of iron will be cobalt. So we are taking 3d7 4s2 like configuration. So if I am taking cobalt plus 2, you will get only 3d7 configuration. If I am taking cobalt plus 3, you will get 3d6 configuration. Okay. Now you take in d orbital there are 7 electrons. It is not half filled or completely filled. In d orbital we are having 6 electrons. It is also not half filled or a completely filled. But even though the cobalt is getting a high positive value, that is standard reduction E naught value is high, plus 1.91. What is the reason for that? Okay, it is not because of the D7 and D6 configuration. It is due to the high charge density. High charge density of cobalt 3 plus ion. It is due to the high charge density and low value, that is low negative value of hydration enthalpy. These two reasons only we are getting the cobalt is having a more positive value. So from that value, so we are expecting titanium, vanadium and chromium as getting negative value of E naught. But manganese, iron, cobalt, we are getting positive value of E naught. So from that one explanation, exceptional behavior is manganese, iron and cobalt. Manganese and iron we are talking about the D5 configuration, but in cobalt we are talking about the high charge density and the enthalpy, that is hydration enthalpy value. So because of that only we are getting what a high E naught value for those metals. So this chapter section we have discussed about the standard electrode potential value of a transition element, that is especially in 3D transition series.